ready to talk about diffraction. But before we do that, let's do a review. And do you remember, what did we call it when a wave changed direction when it bounced off of something? So that was called reflection. Okay, what was it called when a wave would change its direction when it went through a material like water or glass? That was called refraction. And now we want to talk about something that changes its direction when it goes around something. So when it goes around an obstacle, that's going to be called diffraction. So in our first picture over there on the left, it shows a obstacle and then some kind of a wave. So this could be water waves, it could be sound waves, and it's traveling in this direction. And then it's going to encounter this obstacle. What's it going to do? Well, it's going to bend around it. So it's going to do something like this. And so an example of that is on a beach. So the picture that's on the bottom and over to the left shows a beach, and then there is something like a jetty or something that is going out into the ocean. And then notice what's happening as the water encounters that jetty. You see how it's curving around it? Okay, now what would happen if you got two boundaries? So here is some kind of an obstacle's up here, but let's put another one down here. So it's making a hole that the waves have to travel through. Well, this one, you saw it curved like this, and it's going to curve like this around it. So if you were to put the two together, what do you get? So if you have a single slit, it is going to make something that is going to do this. So it's going to make those circle things that are going to get larger and larger. So in the picture that's on the bottom there, on the right, it shows water waves that are having to go through two of those jetties, points. And you see that when the waves go through it, you see how it's spreading out like this, and then look what it did to the shoreline. So do you see that the beach behind it is also curved? So it was carved by the waves coming through that slit. All right, so now let's go back to our simulation here. And so let's turn it on. And this time we want to go to, again, the slits. So let's go to the slits and open it. And we got one slit. So we've observed what happens with two slits. So let's observe what happens if you have one slit. Okay, so there's some light. It's impacting the slit, and you see that it's opening up like this. Now, what could we change about the simulation that is going to alter where you have constructive and destructive interference? So notice that going straight through it, that's constructive. But do you see down here where it's kind of dim? So right here and also right here, that's where you have your destructive interference. So what I want you to do is, let's change the frequency. Change the frequency of the light and observe what happens to where you have constructive and destructive interference. Okay, so I will try it with a small frequency. Kind of hard to see what's going on, but it did change the location of where it's interfering destructively. Now let's try it at the high frequency. Okay, that one's a little bit better, easier to see. So you have constructive interference down the middle, and then right up here again, you've got your destructive interference. So what's another way that we could change the simulation? Well, we could put more slits in there, but we want single slit interference. So what I'm going to do is change the opening right here. So I'm going to change the slit opening. So I'm making it smaller, and look what happens. So it changes again the location of the interference patterns when you do that. I wonder if there isn't a formula that would tell us where the interference, constructive and destructive interference, is going to occur. Yeah, you know there is. All right, so let's get rid of this. Go back to here, and then let's go to our next slide. And here is our formula. So that you have, it depends on n, which is going to be the number of where the, notice this one is minimums. So this is where you would have the destructive interference. And it depends on which n are you interested in. It's also going to depend on the wavelength of the light that you're using. It's going to depend on the slit width, so that's going to be the A, and it's going to depend on your angle. It's going to be the same three things that determined interference. Depends on the wavelength, has something to do with distance, and it has something to do with the angle. Now, you're not going to do anything with the formula, but I did want to show the formula to you, and notice how similar the formula is to the double slit interference formula. Okay, and so let me go back up to here. So we've already seen this, that the amount of bending and where the constructive and destructive interference occurs at depends on the wavelength of the light being used, and it also depends on the width of the slit that it's going through. And then over here is a picture of interference effects of light going through a single slit and then is being shown on a wall. And so I'd like for you to watch this little demonstration demonstrating diffraction using laser light for teachers. So go ahead and watch that little video and see if you can identify where is it constructive and then where is it destructive, and try to figure out for yourself what's causing that to happen. Okay? All right. So now we're finished with diffraction, and so our last segment is to talk about what is polarization. So I'll see you in just a moment.